Yeah, I thought it's about time I gave an update on progress on the 37 Chevy. It's been about a year since I posted anything, so I've been fairly busy, probably since about June of this year. And my goal for this year was to get the suspension functioning, so I think I'm pretty close. I'm gonna walk through some of the things I've done there. It's just a recap for anybody who's not seen the previous videos. 37 Chevy street rod. Want to use it for the racetrack as well, road racing, maybe some autocross. It's mid-engine design. There's a Audi R8 transaxle in the back, and it's all-wheel drive. So there's a front differential. So I want to talk a little bit about the knock-on effects some of the design decisions have had, and they've driven some extra work. So the initial concept was to use a Porsche transmission in the back, just have it rear-wheel drive. But I decided the Porsche transmission was going to be not up to the task of handling all the torque from the twin-turbo engine. So I upgraded to the Audi R8 transmission, and that's had a bunch of consequences for extra work. So early on, I decided I was going to use Corvette front suspension, front and rear. So the uprights are from a C5, and initially I thought maybe I'll just make some custom axles, but in the course of trying to weigh pros and cons, I decided to go with the stock Audi R8 drivetrain instead. So I've adapted the front hubs from the R8 to the C5 upright. So it wasn't just a straight bolt on for sure. So I had to remachine the bolt pattern and sleeve on the inside for the pilot diameter. So I got a little bit more work to do there still, and mount some socket head cap screws for mounting to give extra clearance. And then I didn't want to use, I already had C6 Corvette rims, so I didn't want to use big, thick, wheel spacers to adapt them to the Audi bolt pattern, because that would throw off the scrub radius and affect the front suspension geometry significantly. So and also to make the track width much wider than what I wanted. I wanted to keep it under 2 meters. So what I did was is I cut. I don't know how clearly you can see it. I cut the flange off of the Corvette hubs, and then scalloped the hub for the R8 hub to give clearance for the wheel studs, and then I've just used lug bolts to bolt it on there, and had to drill some clearance holes in the brake rotors as well to clear those lug bolts. That was fairly straightforward work. So that's worked out okay. Yeah, so I decided I wanted to dispense with the Corvette as conventional ball joints, and you can see the wishbone's fairly short, so that affects geometry. You get significant changes in geometry as the wheel moves through its range of motion. You can see, the wishbones I've made here out of chromoly are significantly longer, about almost twice as long, and that's the upper and the lower ones. Same story on the lowers, quite a lot longer than stock, and I could get away with that because the motors, the engine's not up front. So dispensing with the ball joints, what I've done is I've made spacers and bushings out of stainless steel. So I turn these up. These are an alloy called 17.4 pH stainless. So it's a magnetic precipitation hardening grade of stainless. It can be heat treated. So I can harden them up to Rockwell C40 fairly easily. I still have to do that, but that allowed me to mount these spherical rod ends instead. So looks a little funky on the top here with all these nuts. There's two jam nuts, inner jam nut and the outer jam nut, and then this hex in the middle is actually provides me with some adjustment for camber. So it started as these are I think they're called header bolts. They're the industrial plumbing bolts, and the camera's not going to focus very well. But all I've done is these are stainless steel as well, 300 series stainless. I've drilled and tapped a hole in the ends to allow me to mount the spherical rod end. And so here's another example here. So the thread pitch between the inner and outer bolts there, the inner and outer threads are different pitches. So by turning this center hex, I wind up with fine adjustment in and out on that upper rod end, and that gives me fine adjustment on the camber. So that's why I've done that. That way I don't have to take the wishbones off either. So another thing I've done, I made these all these wishbone mounts. So these are also milled out of 17.4 pH stainless, machined out of solid. It's a bit of work, chewed up some carbide end mills in the course of making these, but they turned out nice in the end. And those can be mounted in one of two sets of mounting holes, upper or lower, for both the top and the bottom wishbones. So that gives me some adjustability for the suspension. Right now, I think I'm going to run the lower wishbone with the front in the lower position, and the rear in the upper position. And that'll give me some degree of anti-dive under braking as well. Just that feature of the suspension geometry. So pushrod suspension's got a pushrod mounted to the lower control arm here. Similar adjusting feature. This is actually off an Indy Car here. This particular unit, but similar concept for adjustment. All you do is spin the one hex here, and it moves shorter or longer. It pushes up as the wheel moves up. That pushrod pushes and actuates this belt crank. So one of the features of this style of inboard suspension, also known as cantilever suspension, it affords you some adjustability a number of different ways. So I've designed it to give me rising rate, effective spring rates. So how that's achieved, the pushrod makes roughly a 90-degree angle with the axis between the mount and the pivot. So the pivot's on a 1-inch solid steel bar, welded and braced to the chassis. But it makes a right angle there. So small movements of the wheel will make relatively large angular movements of the bell crank. And over on the mounting end for the shock, it's the axis between the shock axis and the line between the mount and the pivot of the bell crank is an acute angle at right height. So small movements of the wheel, significant movements of the wheel result in small movements of the shock and compression at or near ride height. So it feels fairly soft at ride height. But as the wheel moves up higher, this becomes an acute angle because the rocker rotates and the pushrod makes an acute angle. And this end of the rocker moves down more to a right angle, 90-degree angle with the shock axis. So that means that at higher bumps, small amounts of wheel movement will result in large amounts of shock compression, spring compression. So that gives you a much higher effective spring rate. So that's how the rising rate suspension works. Pretty effective. I got two different mounting holes. They're mounted in stainless bushings here. Set on the outer mounting holes for more for the racetrack. Inner mounting holes will be for street driving. I've got a limited range of motion here, so in the track setting, I think I got it set up for about 2 inches of wheel travel total between bump and droop, and the street setting will be only about 4.5 inches. So it's probably going to be a bit of a harsh ride, but we'll see how that goes. It's not a luxury car. So something else of interest is the this anti-roll device that I've got here. This is out of a late model Indy car. So it's a blade type device, and you can see the this is the blade in the back, and it's adjustable through cable operated from the driver's position, so I can rotate the blade to different angles. And that'll allow me to change the stiffness of the anti-roll action. So in roll, when one shock is compressing, the other is extending. That makes this lever twist, and the twisting motion makes this this blade bend. So obviously, in this setting, full stiff, it's very resistant to bending. And in the opposite setting here, that would be a full soft setting there. So it would be a little less aggressive. In the cab, haven't done a whole lot there. Still got to weld in gussets. I need to pull the cab off of the chassis here so I can get up top and finish the welding inside there. That's another year's project. At the back, I got a similar pushrod suspension. The angle's a little bit different for the pushrod, so I changed the geometry of the bell crank a little bit. You can see how this works here. I'll lift the wheel up here, and it just compresses the bell crank like that, and that's how the pushrod suspension works. Again, chromoly upper and lower wishbones here. I don't know if there's a whole lot more to say that I haven't explained already. It's all aircraft grade fasteners. These are SPS fasteners, so they're about over 200,000 psi strength. So beefy stuff. Maybe it's a little bit overkill, some of it. What else have I done? I've made the adapter plate that's going to double as a bulkhead. I've roughed it together. It's 1.25 inch aluminum plate. I got to take some weight out of this. I need to figure out where everything's going to mount first before I start popping holes and milling pockets in it. But right now that plate weighs about 35 pounds. I need to get it down to about 7 pounds. So that's my goal. Also, I've the transmission. It's from the factory. It would be a paddle shift unit, so it uses Lamborghini calls it e-gear. Audi calls it Artronic, but it would be a electrically operated, solenoid operated hydraulic system to shift gears in the gearbox. So I've changed that over. I bought this manual shift mechanism. Came out of Austria. Lots of parts on this truck are used from eBay. Thank goodness for eBay. I'm up in Canada, so it's pretty hard to get. You're not going to find that at your local parts supply place. So parts are a little pricey, but you can find them. And then the engine. I talked about this last year. So I got Indy Car Headers here. Those are off a Honda, late model Honda, and the twin turbos will mount probably in this area here. People have asked me why the engine's offset on the cab or on the chassis. So it's offset about a little over 2 inches. That's because the cab on the truck is so narrow. The front drive shaft's got to go in between the seats, and the output shaft for the front on this transmission is actually offset about 3.5 inches over from the input shaft. So in order to get the front drive shaft to clear up in the cabin, I had to offset the engine. So with this layout, the front drive shaft actually needs to go through the oil pan of the EcoBoost engine. So I got some work to do there to make up a custom oil pan. I needed to do that anyway for the dry sump setup. So. Anyway, that's a quick overview. I made some decent progress this year, but maybe it's a little hard to see, but there's lots of problem solving and lots of time spent on the mill and my lathe during the course of the summer. So now I'm going to lose the garage to my wife wants to park in here. We got snow on the ground up here in Canada, so I think work's coming to a conclusion for the year here. Next year I want to get I want to get the brakes on this thing, so I've got NASCAR AP Racing rotors from NASCAR to mount on there. I also need to mount the steering, and I want to get the drivetrain working, so I'll get the drive shaft and maybe the oil pan completed, and get all the bearings mounted and everything for the shafts. So anyway, that's an update for the year. Anyway, more to come.